Hello everyone, I'm Ryan, and I am a fusion scientist. But today I want to talk to you about other uses for plasmas, specifically how we can decarbonize the chemical industry with scalable chemistry optimized by plasma electrification. The chemical industry is difficult to decarbonize. That is for two main reasons. The first reason is that it is incredibly fractured. There is no large piece of the pie that we can attack in order to make a large impact. The second is that while we can electrify to eliminate the emissions from fuel, and that is 70% of the emissions, 30% of the emissions come from the process itself. They come from the recipes we use to do our chemistry. And that means we need to rethink how we do it. So what is the cause of these emissions? The reason is hydrogen. There's been a lot of talk about hydrogen in recent years, geologic hydrogen, and a few years ago, the Department of Energy launched the Green Hydrogen Earthshot, trying to bring the price of hydrogen down to less than $1 a kilogram. We never got there. We have still not gotten close. We're at $3 to $6. And that's because that's difficult because we're competing with the incumbent, which is the steam methane reformer. When I say SMR, I'm not talking small modular reactor. Steam methane reformer. 75 cents to $1.50 a kilogram. It's almost impossible to compete. 95% of the 100 megatons of hydrogen that we use per year comes from a steam methane reformer, and it's responsible for 1 gigaton of CO2 emissions per year just in the United States. So, the steam methane reformer is the villain in this story, and it is a pernicious problem. The reason is because it only operates economically at extremely large scales, 1,000 tons a day. And it takes methane and water, it burns some of the methane, and it also converts the methane into hydrogen or syngas. But the real problem is that 1,000 tons a day drags the scale of everything else up to meet it. That means that the Haber-Bosch process we use to make nitric acid, which is a primary component in fertilizer, which is currently stuck in the Strait of Hormuz, that also has to be at 1,000 tons a day. There's $1 billion trade deficit because we don't make enough of this in this country, because to make a new one costs $17 billion. The other thing that it can make is synthesis gas, which we use to make methanol. And methanol is a precursor and used for almost all of our plastic and textile manufacturing. The steam methane reformer is the endothermic step. It's where we put energy in, and then we oxidize everything down afterwards. So in order to change the paradigm, we have to rethink the chemistries that we use. We have to change the recipe, and we have to remove hydrogen from the recipe. With a plasma, what we can do is we can take the air we are currently breathing, run it through a plasma, create NOx, and we can bubble that through water to make single-powered step nitric acid. Plasmas can do this because they do not operate the way thermochemistry does. Instead of breaking the bonds with brute force, we're surgically slicing them, and we're doing it in the ways that allow it to happen at the lowest energy barrier. Other things we can do with a plasma is we can make single-step direct synthesized methanol. This is a holy grail reaction in thermocatalysis that no one can do, because once you break a methanol bond, the molecule is so unstable, it wants to completely fall apart. Plasmas can do this because they can create high temperature zones and low temperature zones and quench the products immediately into the methanol we want. And we can also do recipes that are completely untractable to thermal chemistry. For example, artificial photosynthesis. We can take carbon dioxide from the air and water and turn it directly into synthesis gas, which means we can make decarbonized downstream commodities. All of this comes with the added benefits that plasma reactors operate economically at scales of 1 ton a day or less. They can be decentralized, therefore they have low capex. There's no transportation cost because I'm making it on site, so I don't need to move my hazardous chemicals. And on top of that, they can ramp quickly up and down, meaning they can load follow renewable energy that would be curtailed. So, now is the time to do this, and this is for 3 reasons. The first is that power electronics are getting much better. They are an order of magnitude cheaper than they were a decade ago, and their cost is going to go down 40% in the next 5 years because new fabricators are coming online. This allows us to target the specific mechanisms that we are trying to do. The second is that AI surrogate models have advanced tremendously, and now we can speed up our modeling by a factor of 10,000 in some ways. And then the last one is that we have the capability to do very rapid diagnostics in operando. So while the reactor is running, we can feed data to the AI models, and we can start to diagnose what is happening in these extremely complex environments. This brings me to the SCOPE program. 2 technical areas, $40 million over 3 years. The first technical area is reactor design. 8 to 10 project teams with a hard downscope at 18 months. They have to demonstrate the energy efficiency of their reaction at 1 kilowatt. And then in 3 years, they have to demonstrate it 10 times more energy input, including the balance of plant. The second technical area is we want to provide these teams with world-class diagnosticians so that they can, and modelers, so that we can understand what is happening inside these plasmas. All of this, no hydrogen feedstock, and electricity is charged at 5 cents a kilowatt hour. Teamwork makes the dream work. We're going to have plasma reactor designers and power electronics experts work hand in glove and co-design the reactor and the power delivery system, which has never been done before. And we're going to do it with multi-scale modeling in the loop for rapid iteration. This slide is to show I've done my homework. I've had over 100 outreach calls with over 50 institutions. And we've come up with a set of metrics depending on the chemistry for the efficiency that we're trying to get. With this program, we can address 5% of US annual greenhouse gas emissions and 8% of our total energy use. SCOPE program, decentralized, decarbonized abundance, powered by plasma chemistry. Thank you.